change your slides?
Yes.
Okay, are you ready?
Yes, thank you.
Okay, so the last speaker of this session is Francesco Mele, and he will be talking about restoring quantum communication efficiency over high loss optical fibers. Please.
Okay, thank you. This is a joint work with Ludovico Lami and Vittorio Giovannetti. And the goal of this talk is to understand how to reliably transmit qubits across long optical fibers. The problem is that until today, optical fibers have not been able to transmit qubits over long distances. This impossibility comes not only from technological limitations, but also from more profound theoretical reasons. However, these theoretical reasons rest on assumption, the so-called memoryless noise assumption. Under this assumption, the noise which affects the signals traveling across the optical fibers, this noise acts identically and independently on each signal. In other words, under this assumption, the noise is statistically the same. However, it has been experimentally verified that this assumption is not always true. In particular, it is false when the signals are separated by a sufficiently short time interval. In this case, memory effects in the noise arise. There is a possible known solution to the problem of transmitting qubit across long optical fibers, which is the solution of exploiting quantum repeaters every few tens of kilometers along the optical fiber. However, this solution is expensive. Our solution does not need quantum repeaters. Instead, our solution exploits memory effects in optical fibers. The basic idea is that the noise can be influenced by the signals sent before. We derive two main results. The first main result is that by properly taking into account the memory effects in our model, unassisted quantum communication is possible at a fixed qubit rate for all non-zero values for the transmissivity of the fiber. And the transmissivity of an optical fiber is typically exponentially decreasing in the length of the fiber. And this fixed qubit rate is independent of the transmissivity. Our second main result says that entanglement assistance and the proper memory effects exploitation allows one to completely neutralize the effect of noise in classical communication. The scenario of quantum communication theory is the following. Alice wishes to send information to Bob across a noisy communication line. The noise is mathematically characterized by a quantum channel, which is a suitable map between the space of density operator of the signals that Alice sends in the channel and the space of density operator of the signals that Bob receives. Across a quantum channel, it is possible to transmit different types of information, qubits or bits. And for each of these possibilities, there is a notion of capacity of the quantum channel phi, which measures the usefulness of the channel to transmit the type of information desired. If the goal is to transmit qubits, one defines the so-called quantum capacity as the maximum over all the possible strategies of encoding and decoding of the so-called qubit rate, which is the ratio between the number of qubits transmitted with zero error and the number of uses with the channel. Analogously, if the goal is to transmit bit, one can define the classical capacity. If Alice and Bob can exploit pressured entangled states in their encoding and decoding strategies, one defines the entanglement-assisted capacities. And in these figures, I have implicitly assumed the memoryless noise assumption. Indeed, I have the noise as represented by the same quantum channel phi. Now let us talk about the communication scenario we deal with in our works. The quantum information carrier, the signal, is a single mode of electromagnetic radiation with definite frequency and polarization. this system is associated with the Hilbert space of a quantum harmonic oscillator. Now let us define the quantum channel. To do so, we first define an environment, which is a single mode like the system. And we fix two parameters, a parameter lambda, which is a number in 0, 1, and an environment state, sigma. A general alternator phi of lambda sigma is a quantum channel, which is defined by its action on the input state in this way, where U of lambda is the beam splitter unitary, where A and B are the annihilation operators of the system and of the environment respectively. The beam splitter is a semi-reflective mirror. The general alternator phi of lambda sigma acts on the input state rho by mixing it with an environment state initialized in sigma through a beam splitter of transmissivity lambda. And the output at this arm of the beam splitter is the output of the general alternator. And roughly speaking, lambda represents the fraction of the input state which is transmitted from the input to the output. For example, if lambda is equal to 1, if lambda is equal to 0, then the channel is completely noisy. And hence the capacities are always 0 if lambda is equal to 0. And if lambda is equal to 1, is that the channel is noiseless. In other words, the channel is equal to the identity map. Since in practice, Alice can produce only those input signals which satisfy an energy constraint, since in the laboratory we have a finite energy budget. In this scenario, one talks about energy constraint capacities, which are defined as the previous capacities, but the strategies, the encoded strategies are restricted only those strategies which whose input signals have satisfy an energy constraint, where N capital denotes the energy budget available in lab. Now, let us talk about optical fibers. In the best studied model of optical quantum communication, optical fibers are represented by thermal attenuators. Thermal attenuators are a particular family of general attenuator where the environment state sigma is a thermal state. And it turns out that the quantum capacity of the thermal attenuator vanishes if the transmissivity is lower than 1/2. This means that sufficiently long optical fibers cannot transmit qubits with 0 error. However, in this paper, a phenomenon dubbed diode quantum communication has been shown. And this theorem says that for all values of the transmissivity, there exists a suitable environment state such that the quantum capacity of the corresponding general attenuator is larger than a positive constant. And this result holds even if we put an energy constraint at the input of the channel. In words, this result means that by choosing the environment state, by manipulating the environment state, quantum communication across this general attenuator is possible even if the transmissivity is very low, non-zero, but very low. And now let us talk about our results. Overwhelming numerical evidence suggests the validity of this conjecture, conjecture 1, which can be regarded as an entanglement-assisted version of the effect of diode quantum communication. The conjecture says that for all values of the transmissivity and for all values of the energy constraint, there exists a suitable environmental Fock state such that the energy constraint entanglement-assisted classical capacity of the corresponding general attenuator is larger than the classical capacity of the noiseless channel. And this conjecture is not a conjecture in the seemingly worst case when the transmissivity tends to 0, because we have a proof of it. And in words, this result means that by consuming pressured entanglement and by controlling the environment state, it is possible to communicate with the same or even better performance than the unassisted case of absence of noise. And in order to show this result for sufficiently small transmissivity, non-zero values of the transmissivity, we have introduced a novel method to easily deal with the calculations involving thermal attenuator. The thermal attenuators are really important in literature because are the standard model to describe optical fibers. However, calculating the output of the thermal attenuator is often cumbersome. For example, if one needs to compute the von Neumann entropy of the output of a thermal attenuator, if the input is a Gaussian state, then the calculation of the entropy is easy. However, if one needs to compute the von Neumann entropy of the thermal attenuator applied to a non-Gaussian state, then the calculation is difficult. And we overcome this problem by introducing a trick that we dubbed master equation trick. And we derive a simple Krauss representation of the thermal attenuator, exploiting the associated Lindblad master equation. And this allows us to obtain simple expression for the output of the thermal attenuator and for the evaluation of the entropy for particular non-Gaussian states. And this trick can be generalized also to other fundamental Gaussian channels, such as the thermal amplifier and the additive Gaussian noise. Now, the Dayard quantum communication phenomena and its entanglement assist version established that the control of the environment state guarantees very good communication performances. So in order to give a technological value to these results, we need to reply to this question: how to implement in a realistic way the control of the environment state? We reply to this question by exploiting memory effects in optical fibers. Memory effects in quantum communication theory can be described by the model introduced in this paper. The model is the following. The channel environment the environment is split in two parts. A local part E, which is the single mode environment which we have considered so far, and also a huge reservoir, a remote part of the environment. This huge reservoir R induces a thermalization process onto the environment, and this thermalization process tries to reset the environment into the initial thermal state. And at the same time, the environment, the local environment, is altered by the signals sent by Alice through the beam splitter unitary. And so we have this collisional model. And the thermalization process is characterized by a one-parameter family of quantum channel, where the parameter is a time interval delta t. And this quantum channel satisfies the following conditions: that if the time interval is larger than a certain thermalization time t with t, then the quantum channel resets the environment into the initial thermal state. And if the time interval is very, very small, then this quantum channel acts like the identity map. And in the paper, we formalize this condition by using the energy constrained diamond norm between this quantum channel and the identity map. And I want to remark that this model reduces to the thermal attenuator model in a particular case. Indeed, if the time interval delta t between signals sent by Alice is sufficiently large, then the environment has enough time to reset into the initial thermal state between subsequent signals. And so when a signal interacts with the environment, the signal sees the environment initialized into the thermal state. And so the input-output relation is implemented by the thermal attenuator channel description. And so the memoryless noise assumption is recovered. In the opposite regime, when the time interval delta t is sufficiently short, then the environment has not enough time to reset into the initial thermal state. And so when a signal interacts with the environment, then it does not see the thermal state, but it sees an environment which is in a state which depends on the signals that Alice has sent before. In other words, there are memory effects. And in this regime, Alice can exert a certain level of control onto the environment state. Let us put this idea together to devise a protocol that we dubbed noise attenuation protocol. The protocol is the following. Step one, Alice waits for a thermalization time so that the environment can reset into the initial thermal state. And the goal of the protocol is to obtain a general attenuator phi of lambda sigma, which is less noisy than the initial thermal attenuator. And so the step one, Alice only waits for a thermalization time so that the environment can reset into the initial thermal state. And at step two, Alice sends k signals, dubbed trigger signals, separated by a time interval delta t, initialized in a suitable state. And these k trigger signals do not encode the information, but are only sent to alter the environment in a suitable way. And step three, after a time delta t, Alice sends an information carrying signal, which interacts with the environment altered in a suitable state sigma. And then she goes back to the step one unless the communication is complete. And we only consider those environment states sigma, which can be achieved by the noise attenuation protocol. In other words, we consider only those environment states sigma, which can be obtained as the environment output by sending trigger signals. If rho k is the state of trigger signals, then after the interaction between each of these k trigger signals with the environment initialized in the thermal state, then the environment can be written in this form, where U is the beam splitter unitary, which couples the signal and the environment. And then we have to take into account also the thermalization process which acts on the environment. Delta t, since the time interval between subsequent signal is delta t. And we need to choose rho k carefully in order to achieve an environment that which guarantees good communication performances. And we prove this theorem that if Alice sends sufficiently large number k of trigger signals separated by a sufficiently short time interval, initialized in a suitable state, then the environment is altered in a state sigma, which satisfies the phenomenon of diode quantum communication. That is that the quantum capacity of the corresponding general attenuator is larger than a positive constant, even if we put an energy constraint at the input of the channel. And this state of trigger signals can be produced by using linear optics and Fock states. And what I mean that this state sigma can be written in this form for a suitable choice of rho k, and delta t sufficiently short. Now, there is a drawback in the previous construction, since we need to take into account also the trigger signals in the evaluation of the rate of the protocol. And the maximum rate achievable by adopting the noise attenuation protocol with k trigger signals sent to alter the environment into sigma is the ratio between the quantum capacity of the general attenuator obtained at step 3 and k plus 1, where k is the number of trigger signals. And the previous theorem may require k to be large. And if k is large, this ratio is low. Fortunately, we show that just k equal 2 is enough to activate the phenomena of diode quantum communication if the transmissivity is non-zero but sufficiently small. We prove this result. It can be regarded as a cheaper version of the previous theorem. Suppose that the transmissivity is non-zero but sufficiently small, and suppose that Alice sends 2 trigger signals separated by a sufficiently short time interval delta t, initialized in this state of 2 trigger signals. Then the environment is altered into a state sigma, such that the phenomenon of diode quantum communication holds. That is that the quantum communication of the general attenuator, the corresponding general attenuator, is larger than a positive constant. And we have generalized these results to the entanglement assisted scenario. And the result is that if conjecture 1 is true, then the noise attenuation protocol allows one to activate the entanglement assisted version of the phenomenon of diode quantum communication. That is that the noise attenuation protocol allows one to alter the environment in an environment state sigma, such that the energy constrained entanglement assisted classical capacity of the corresponding general attenuator is larger than the classical capacity of the noiseless channel. And by exploiting memory effects, which can be described by the model we have presented, we can activate this phenomenon of diode quantum communication to enhance the performance, to improve the performance of communication. And the take-home message of this talk is that memory effects are not bad. Instead, memory effects can be engineered to improve the communication performance. And in the model we have introduced, the noise attenuation protocol allows arbitrary long optical fibers to reliably transmit qubits at a fixed positive rate and bits and qubits at the maximum achievable rate in the noiseless scenario, provided that pressured entanglement is consumed. Thank you for the attention.
Thanks a lot, Francesco, for this very nice talk. We have enough time for a few questions. So perhaps I have a naive one. So you have this interval delta t, right? It's to ensure that you have this memory effects. Do you have any quantitative bounds on how small this delta T has to be, or is there a way to quantify this?
We have not a quantitative bound on how short has to be this time interval, but we are establishing collaboration with experimentalists to try to estimate this thermalization time below which these memory effects arises. But we can try to use we can have a rough estimate by reading the usual repetition rate that are used in the nowadays quantum communication platform, which I think that they use a repetition rate of the order of 1 gigahertz. So I think that this time interval has to be less than 1 nanoseconds.
Okay.
And but we are trying to establish an experimental collaboration too.
Okay, sounds good.
Thank you.
Do you have any other question? Okay, then if not, let's thank Francesco once again. Thank you very much.
Thank you.